Alright, let's see. So, reminders. Your final mastering is due on Monday. That's Chapter 19 mastering. We're going to review for the final on Monday. Your final, let me write it up there. Friday, 8 a.m. in here. And student evaluations, as of 5 minutes ago, we are at 70%. So we have until class time Monday to get to 95%. Alright, there you go. Alright, those are all my notes. Let's go. Let's finish up chapter 19, talking about a few. We're going to watch some videos today because I felt, why not? Alright. So positron emission is the last type of nuclear reaction we're going to be concerned about. Positron emission occurs when an unstable nucleus ejects a positron. So, what is a positron? A positron is the antiparticle of an electron. Sounds like super science fiction, right? The antiparticle. It has the same mass as an electron, but it has the opposite charge of an electron. So what charge should a positron have? Positive. Excellent. That's where they get the name from. So a positron is symbolized like that. Alright, so similar to an electron, that has no mass, but it's going to have a +1 charge. So it's not a neutron, because a neutron would have mass. And it's not a proton, because the proton would have mass and charge. So this is a positron. So when you have a positron and an electron collide, what should I make? One of the previous choices. Okay, let's add at the top. What's 0? +1 minus 1 is 0. What's our 0, 0? Their gamma ray. Which means when they collide together, they're going to give off this ray. This energy is emitted. So where this comes into importance is what's called a PET scan or PET scans. Oh, I lost my page notes on it. So PET scan stands for positron emission topography, which means as positrons are being emitted, they scan the person in 3 dimensions to see where the positron is being emitted from. That way they can see where, in most cases, the cancer is at. So, let's watch a little video about how that works.
Scan creates 3D images of the body. It does this by using radioactive tracers, which are usually administered to a patient through intravenous injection. The tracers are made up of carrier molecules that are tightly bonded to a radioactive atom called an isotope. The carrier molecule can interact with or bind to specific proteins or sugars in the body. The carrier molecule that will be used depends on what the doctor is looking for. If she suspects cancer or is monitoring a known cancer's growth, she may use FDG, a modified form of glucose, which gets absorbed by tissues. When tissues absorb a lot of glucose, it may indicate a cancerous tumor. The radiation from the tracers poses little danger to the patient since they quickly pass out of the body. The isotope produces small particles called positrons, which interact with surrounding electrons. This interaction results in a complete annihilation of both particles, releasing two photons that speed off in opposite directions. The detectors in the PET scanner measure these photons and use this information to create an image of the distribution of FDG in the body.
Look at that, Gen Chem is a big deal. Yeah, I didn't even know Gen Chem, and we're talking about PET scans. Alright, so PET scans is one way that we can use this kind of technology. Other things we can do with radiation are other areas of nuclear chemistry, like electron capture. So electron capture technology is where a particle being absorbed instead of ejected from an unstable nucleus. So it's kind of the opposite of the positron emission. Alright, so in this case I have a proton and an electron. What will they come together and make? Light them up. What has a mass of 1 and a charge of nothing? Neutron. So in this case, I am going to shoot an electron at an atom to make something new. Alright, so I could do this with I could take an element and shoot an electron at it. And change its net proton amount. Right. I haven't changed actually the number of protons. I haven't taken one out or put one in. But by slamming the electron into it, it makes it appear as though it's a different element. So this is like the super colliders that you hear about, maybe in your average everyday conversations. Maybe not. Maybe they don't pop up very often. But super colliders, what they're doing is this: they are slamming electrons into elements to try and make new elements. There you go. Similar, except this is we are forcing two elements to push together. Yep. Yep. So anytime you hear about super colliders, this is what they're doing. They are speeding up. Imagine like a NASCAR racetrack, right? They go like this. Except it's usually like 10 miles around. Very, very skinny tube. And they speed up electrons to almost the speed of light and try and slam them into atoms to make new elements. Why? Part of it's figuring out how much energy is required to do that, what makes a new element. Like, we know theoretically it has to do this, but why are there only 92 naturally occurring elements on Earth? Are there other elements that could be stable and we just haven't found them yet? Or maybe there's elements out there that are so unstable we can't, dig them out of the ground. And maybe some of these new elements they find could be a potential energy source, because if they're not stable, right, when they fall apart, they emit particles and energy, and maybe that energy is renewable to the point we wouldn't have to use fossil fuels. That's kind of the idea behind all of these things, that if we can find an element that is stable enough that you can transport it, but then it's willing to decay, you could use it in power plants. All right, pros and cons about that, obviously, but we'll talk about here in a little bit about nuclear power in general. So, electron capture. All right, that's all good, but you know what I love to do besides graph? Calculate let's talk about first order kinetics. Let's have a Throwback Friday topic. Is it too dark in here? I feel like it's really dark. Okay. There we go. Oh. I'm getting sleepy up here. Alright, radioactivity is, in general, right, the spontaneous emission by unstable nuclei of either a particle or radiation to get to a stable configuration. All of this decay is first order kinetics. So remembering our first order kinetics, this hopefully looks vaguely familiar. Alright, that was our half-life statement. And then K is our rate constant. Okay, the other version of this we use was that. Which in this specific case, NT is the number of radioactive nuclei at time T. And N0 is the number of radioactive nuclei at time 0. Right, so a ratio of how many are left is a function of how long did the experiment go and the rate constant of it. Alright, so if you go forever, that number will be small compared to the initial, right, because eventually they decay off. Let's see, can I have this on the next page? No. Alright, where do we most frequently come across these kinds of comparisons? This technique called carbon dating. Alright, everybody's probably heard, like, way back in elementary school, oh, we know how old this bone is from dinosaurs based on carbon dating. So what does that mean in terms of radioactive decay? So if I have, let me get this right. What is typically the mass of carbon? 12. Good. Thanks. Okay. If you don't know that, that's all right. All right. So carbon typically has a mass of 12. So what would I call this relationship to regular carbon? It's 14. Starts with an I. They're isotopes. Excellent. So this is an isotope of carbon. That is fairly stable, but over time, it would decay down to the actual stable nitrogen and an electron. The half-life for this carbon to decay to nitrogen is 5,730 years. Slow. Right? On a scale of things we normally look at, it's on the slow side. So if we know the ratio of the two types of carbons, we can then go in and figure out the age of the sample. A pretty good estimate, at least, the age of the sample. So let's do that. So let's say you're out and about and you take a tree sample. And you measure that tree sample and it has an activity of 10.1 atoms per minute of carbon. If you have a living tree that has a decay rate of 15.3 atoms per minute, let's figure out how old your tree is. So it's really a two-part kind of question. First, we have to find our rate constant for carbon, right? Alright, so using that equation, 0.693 over T1 half. Because T1 half for carbon is unknown. It's 5730. Double check my math, make sure I'm right. Alright, so that's going to be the rate constant for carbon decay. So now I can actually go in and use this K and this ratio to figure out how long the tree has been dead, I guess. No longer living. Alright, so this is our NT, right? This is our old tree, and this one is our current tree. Alright, what should I do first? Of all the mathematical options in terms of operations, what's the first one I can do? Okay, right, find this division and do the natural log of that to start. Alright, so then how do I get the time by itself? Do I add it? Do I subtract? Okay. Alright, you divide both sides by it, and you should end up with like 3,500-year-old tree. Alright, so that's in general how carbon dating works. There's obviously some more technical details to it. Alright, so that's pretty straightforward and easy. Alright, you just plug it into the coop. So let's obviously make it trickier. Okay, you may not know this, your smoke detector has americium-241 in it, which is a radioactive isotope of americium. And it has a half-life of 432 years. Well, let's figure out how long will it take for 1/3 of the americium to decay. So let's think through what it's asking, right? If it's 33% decayed, how much should be remaining? Okay, good. Okay. I understand we're getting towards the end of class and everyone's brain is probably fried, so that's why we're doing easy math. Okay. So if it's 60, how do I figure out how much is remaining? So if I say I have 1 half-life. If I'm at 1 half-life, how much is remaining of my original compound? 50%, right? If I'm at 2 half-lives, how much is remaining? 25%. If I'm at 3 half-lives, right, 12.5%. Okay, so the half-lives are related to the percentages. They are related through this 0.5 to the n. So if I have 1 half-life, it's 0.5 to the 1. If I have 2 half-lives, it's 0.5 to the 2. If I have 3 half-lives, it's 0.5 to the 3. Right, so the n is our relationship of how far away from the half-life we are. T over T half. Alright, so let's work on solving the problem then. Alright, so if I have this equation, fraction remaining is 0.5 to the n. Do I know the fraction remaining? Yes. How do I turn my percent into a fraction? I'm just going to leave it like a decimal. So I could do 67 over 100. This is like the tricky math, right? Because now I need to get the exponent by itself. Alright, so the fraction remaining is some number of half-lives. I'm trying to figure out how many half-lives. Try to figure out n. So what do we know mathematically that moves the exponent from the exponent to in front of the parentheses, log? So log of 0.67 equals n log 0.5. So let's see what it's out. Log of 0.67. Right, so that's how many half-lives it'll take to get to 67% remaining. So now I'm going to plug it in here and figure out how many years that is. Right, so I'm saying 0.58 equals how many years compared to, I know 1 half-life is 432. So it'll take about 250 years to get to the point where it's 1/3 gone or 2/3 remaining. Those are the only two really mathematical questions I can ask you about half-lives. So if you can do those two, you can do the homework for Monday. No problem. Questions about that? In that case, let's watch more videos. Alright, let's talk about fission. Alright, so late 1800s, early 1900s, Enrico Fermi tried to synthesize a new element by bombarding uranium with neutrons. He was trying to do this. Right, he was trying to enhance the uranium to get it to be unstable, to then make a new element, like just eject a single electron. You didn't know that. That's not possible. Instead, what he found was this. He found that uranium by itself will uranium when hit with a neutron will spontaneously fission into other elements and release a crap load of energy, a ridiculous amount of energy, enough energy that maybe you could make a bomb out of it. He was surprised the first time. Yeah, he was not expecting any energy to come out, right? He was expecting a new element, an electron, and instead, his experiment kind of blew up on him. I mean, at the time, they were using uranium without any safety protection. We had a whole bunch of other issues going on, right? I mean, he's just, if you're imagining Star Trek 2, right, where Spock goes into the center, okay, no one's, okay. Oh, yes, okay, right. So this is kind of like a small version of that. So they ended up with terrible radiation poisoning because they didn't know that these elements were causing their cells to go crazy, either burning off or causing cancer, sometimes a little bit of both. Because they were just moving around with their hands. At the time, it was not known that you shouldn't taste things to identify them. So a lot of the experimental procedures, you put it on your tongue and you would see if it was salty, then it's probably an ion. If it was bitter, it was probably this other compound. And so there was a lot of, which is why if you ever read the lab safety things, it says don't pipette by mouth. It's because they didn't used to have those rubber bulbs. You would just put your mouth over the pipette, suck up like a straw, and put your thumb over it. They didn't think anything was wrong with that. That was very standard scientific procedure in the early 1900s. So we've come a long way. So if you ever read it and it says don't pipette my mouth, it's because that used to be the standard of how you pipette things. So, and I've seen you guys pipette. You guys are not good. You would have stuff in your mouth all the time. It would be not good, right? Because you always have to over pipette so that when you get your thumb over it, it is at the line, and so most people like stick it into their mouth and then just spit out the excess. Anyway, that's a fun fact. Alright, so this uranium-235 undergoes this chain reaction in which neutrons are produced and it induces the fission of other uranium. Right? So when this happens, if there's other uraniums around it, it chain reacts. And so more uraniums react, and then more uraniums react. So, let's talk about nuclear weapons.
I have here a scale marker of the first atomic bomb ever used. This bomb, which destroyed Hiroshima, contains about 60 kilograms of uranium-235, of which only about 600 grams underwent fission. Enough, though, to generate an explosion equal to more than 13 kilotons of TNT. The bomb's designers divided the amount needed into two pieces. At the tip, they placed about 40% of the necessary uranium. They loaded the remaining 60% with uranium. Conventional explosion drove the projectile into the target, initiating the nuclear explosion. Now, the exact details of this bomb remain classified because it could still be used. Although this design involves some brilliant innovation by engineers of the 20th century, the really difficult part is preparing the uranium. This lies at the heart of all efforts to stop the spread of nuclear weapons. The key problem? Separating two nearly identical variants of the element uranium. Natural uranium occurs as a metal ball that contains primarily two isotopes. Most uranium is U-238. U-235, however, can easily sustain a chain reaction that produces tremendous energy, whereas the more common U-238 does not. Most elements are stable, so when bombarded with neutrons, they simply absorb them and decay later, or they require very high energy neutrons, but bombarding U-235 with low energy neutrons causes its nucleus to split. The emission of these extra neutrons allows for initial fission to generate a chain reaction. So, how do we go about enriching the U-235 in natural uranium? When we separate two items, we have useful differences. The two major uranium isotopes have identical magnetic and chemical properties. No magnet will tug on one more than the other. No solvent will wash away only one isotope, and neither will boil before the other. So to separate them, engineers discovered one small difference between them. U-235 weighs slightly less than U-238, less than a 2% difference, just enough to make separation possible, but not easy. That tiny weight difference means that the two isotopes will move at slightly different speeds to expose to an equal force. To enrich uranium for the first atomic bomb, engineers built a mini gaseous diffusion plant to capitalize on the difference in speed. A gas containing uranium flows through miles of piping at a tiny rate, but the lighter U-235 wins out. The gas flows through a tube and paste in a chamber. A pressure difference between the chamber and the tube causes more of the U-235 to pass through perforations in the tube. To increase the separation, the slightly enriched stream in the chamber is passed through many more stages like that. To enrich 3% U-235, 90% takes nearly 4,000 stages. Enriching uranium for the first atomic bomb required a diffusion plant that heavy over 40 meters. It houses a maze of 100 miles of piping. These diffusion plants use great amounts of energy to run, compressors generating the pressures needed, and the energy to heat gas flowing through miles of tubing. Another method of separation is close to small mass difference by using a cylinder. A typical device consists of a stationary outer cylinder and an inner rotor that spins. A gaseous mixture of the two isotopes flows up a tube along the central axis, filling the rotor. As it spins rapidly, more of the U-238 is thrown out to the edge than the lighter U-235, which stays closer to the middle. The enriched stream can be removed from the rotor and sent to another centrifuge to be separated even more. The amount of separation is exaggerated here. In an actual centrifuge, the amount of enrichment is a fraction of a percent, so a typical plant might have 60,000 centrifuges to enrich natural uranium to 30% U-235. Such a plant uses 4% of the energy of a gaseous diffusion plant. Even though this is a much more efficient process, the precision that the rotor needs to be manufactured with makes it very difficult to engineer. The smallest defect is the rotor spins itself to pieces. That's lucky for us, otherwise we might have nuclear devices right next to our microwave oven. I'm so happy to engineer. This video is based on a chapter in a book.
Alright, so when they're talking about nuclear proliferation, especially in the news right now, where they're trying to get countries, Iran, for instance, to not get their critical mass, they are trying to prevent them from building centrifuges to purify U-238 into U-235. U-238, great for a nuclear power plant, no problems. 235, the only use for it is nuclear weapons. And so when they're talking about that they find these plants in Iraq and Iran with centrifuges, the only reason to have a centrifuge of that style is to enrich your uranium. And right now, they are working on a treaty with Iran and Iraq to try and figure out, hey, you can totally have nuclear energy, we don't have a problem with having a power plant. The issue is, we still want you enriching your uranium. We don't trust you guys with nuclear weapons. That's really what it comes down to. North Korea does have a centrifuge plant. They are trying to make their own nuclear weapons right now. I think most because North Korea doesn't care what anyone else thinks. They're going to build their power plants, and they're hoping to regain South Korea as well as some other countries around them. So, as you're watching the news in the next few weeks, pay attention to how this works, because now you can explain to the people around you, hey, this is why they're concerned about centrifuges, or why they're concerned about when they say nuclear proliferation, that is what they're talking about, building up a critical mass, because, right, you have to have 600 grams or so, which is, I mean, seemingly not a lot, but you can see all the work that goes into making it. 600 grams is all it takes to make one atomic weapon. So, as informed voters, pay attention to your news, right? It's a Debbie Downer most of the time, but it's good to know what's going on. Alright, why don't we change gears and talk about nuclear power as a good use of nuclear energy. Alright, so fission could be used to make a bomb, right? In which case the energy is all released all at once. But if we control the reaction, slow it down, we can harness the energy in little pieces and use that energy to turn the turbines to make electricity to power your house and your phone and your computer and whatever, right? So, let's see. Right, so if we're able to slow down the reaction to the point where we can collect little bits of energy at once, right, not looking to blow up an entire city, just little tiny pieces at once, I can use that energy to turn my turbine to, right, generate electricity the traditional style. So instead of using coal factories, right, so a coal burning power plant burns coal to turn water into steam, the steam turns the turbine. Or if it's, you know, what's the other kind of thing? Coal, solar, you use a solar plant, which is fairly hypothetical. Same thing, you could use the solar energy to heat the water, to turn steam. So in all the cases, you need some input of energy to turn water to steam that turns the turbine. This is just one option of ways to do that. And the biggest asset they have is that it doesn't take very much energy to get these plants up and running. And they don't have any emissions out to the air, right? Which is the thing we're always concerned about, right? There's no smoke, there's no carbon dioxide, there's no toxic fumes coming out of it, so it's all contained within the nuclear reactor. Trade-off being, people are frightened of anything that's nuclear power, because in their head, nuclear power means Manhattan Project means they're looking to blow up the city. Misnomer. As you guys all should be informed now, right? This is a very safe method of using it. The only other concern we have is what to do with any radioactive waste that's left over. And that's an ongoing problem with all kinds of waste, right? You guys make waste in the lab, right? You pour it into the waste container. Have you ever thought where that goes? It goes into a barrel. Some company picks it up, the barrel gets put underground, and we just put some dirt over it. That's it, problem solved. And so you make as much waste as these power plants do. I mean, and the issue is we don't know what to do with it. So right now, we just bury it. So that's going to be an ongoing issue, because right at some point, we're going to run out of space of things to bury. And there's only so many poor countries that are willing to have us put our garbage in their country. That's often what the time is. Like a country that doesn't have a lot of money will be like, you know what, we have a lot of land. You ship us your toxic waste, we'll bury it, you pay us. And that is ways for that country to earn a lot of money. Right, there's some trade-offs there. Obviously, they are putting at risk their country, but they need the cash flow. I'm super Debbie Downer today. Yeah. So that is another fun fact about chemical waste. And so right now, nuclear waste is such a small issue in terms of chemical waste in general. So I don't know if you guys have been to a landfill lately. They're better than they used to be, right? But there's only so many places we can put our garbage here in the U.S. So sometimes they take it out to sea and they dump it. And they bury it out in the ocean. Who doesn't complain? Whales, maybe? The occasional dolphin that learns to speak. Flipper, like the lassie of dolphins, will come over and chat us about it. But so yeah, this waste issue is not getting any less to be an issue. In fact, it's a bigger issue as we go on. So I'm a big proponent of nuclear power. I think the amount of waste it produces is very small compared to the energy it makes. It's a clean form. I know they're building one here in South Georgia. Don't be scared of it. It's going to be fine. It's going to make lots of power. And the trade-off is that, right, it's not going to put anything up into the air, which is the other issue, right? We could just burn all of our waste. That is an option. We could just send all of our chemical and landfill waste to the incinerator and burn it. Trade-off there, right? I mean, Abigail. Yeah, so they had a terrible combination of things happen to them, and that they were not expecting an earthquake and tsunami to happen at the same time. They were really prepared for like one or the other. And the tsunami was the bigger issue in that it swamped their nuclear plant, like it was underwater. And they have admitted they should have built a higher seawall. It shouldn't be so close to the ocean. There's some traps there. But, I mean, there wasn't a huge spill. there wasn't, they evacuated out of precaution. It's actually totally safe to move back in. A few workers died, but I mean, less workers died at that than in the traffic accident that just happened, right? 6 or 7 people died in a traffic accident. That's how many workers were killed by the nuclear power plant thing. So comparatively, nuclear power is pretty safe to work at and to generate electricity. So, again, since you guys are voters, and this is going to come up in the ballot, again, whether or not nuclear power should be allowed in Georgia or we should vote it down. Think of your options. Chris. Yeah. They're super interesting. They'll give you tours. There's a power plant. Which direction are we? In the west of here, towards Alabama. There's a power plant. We have lots of Berry College students who work there. I'll give you a tour. It's interesting. It's a coal fire plant. And so, you can see it. Smoky sometimes. Now, not like black soot. But I mean, they have scrubbers in their towers, so they give off mostly clean air. It would be similar to that. Yep. Yep. So yeah, there's some power plants around here. The one you smell is the paper mill. No, there's a paper mill around here, and so that is just the way it processes paper. That's a whole different set of issues over there at the plant making paper. And it's because everybody likes their paper white. If you didn't mind that it was off color, it wouldn't smell. It's the bleaching process, because nobody wants paper that's not bright white. And so if you were okay being like slightly tan paper, then the smell would be gone. So, anyway, something to advocate, right? Less bleachy paper. So. Alright, let's talk about let's see, what else do I have left? Nuclear fusion. Estimate 300 years. It's a pipe dream. As of right now, we don't have the technology, nor is the technology on the horizon to do fusion. Fusion would be the best possible energy source, because all you do is you slam 2 helium atoms together and make energy. We have lots of helium. And it makes tons of energy with no other products. It'd be amazing. But it's so hard. You have to put so much energy into the helium to get them to slam together that you don't gain any energy in the output. Right? So right now it's net loss. So if you ever hear about nuclear fission, it's in theory. In theory, nuclear fission should absolutely work. Realistically, we don't have the ability to do it. And you might hear about cold fusion. Crazy thought. It means that the helium wouldn't have to be heated up, which, as you know, the relationship between heat and energy, if you need high energy helium particles, it's typically super hot, high pressure in order to get them slammed together. So cold fusion is the idea that you could do it at room temperature, which everything you know about Gen Chem says that's probably not possible. So cold fusion is great for the movies, not realistic. Alright, let's see what I can get through in my last 5 minutes. I think I can. Alright. Radiation in everyday life. We talk about RADs and REMs when we're calculating radiation in everyday life. So as of right this second, you're being exposed to radiation. All the time. There's radiation coming from the sun, radiation coming from all kinds of sources. But there are certain types of radiation that are more dangerous than others. So there is alpha radiation, alpha particle radiation. That's not spelled right, but everyone knows that word is dangerous. I look my little bit of unable. Anyway, super dangerous, but luckily you have skin, and your skin prevents it. It just hits your skin and bounces off. Because it's such a big particle, it can't get into your body. Could be skin cancer. That's different. All right, different thing over there. This would be the worst type of radiation to be exposed to if you didn't have skin. But luckily, I think everyone in here is majority skin, so you're good. Beta particle radiation. Moderate danger. I mean, on the scale of danger, it's like, not great. You don't want to purposely expose yourself to it. You'll get a radiation burn. But you would have to actively seek out these sources. Like, you'd have to go get a bunch of x-rays over and over and over again without the little shield on you, right? Or purposely sign up for a bunch of PET scans. Just have them do it over and over and over and over again, right? You would have to seek out this sort of radiation in order to have an issue with it. All right, so what I want in my last minute, what do I want to tell you? Look at this. All right, radiation. So if you live in the U.S., which I think all of you do most of the time, so on the scale, we're talking about millirems. To get radiation poisoning, you need 100 rem. Look at the scale, they're all in millirems. So how many millis are in a whole? 1,000, right? So if it's 2.5 millirems, it's really saying it's 0.002 rem. You need to get all up to 100. So everything you do in average day of life, right? Stand outside, go on an airplane ride, even if you do something crazy, like have the thallium heart scan where they inject the thallium dye into your heart and then watch it beat, that's still only 500 millirems, 0.5. No, the radiation, you pee it right back out. Like it decays in your body and then you just excrete it as regular non-radioactive stuff. So you would have to do something crazy. Yeah, JT. It's on the millirem scale. I mean, the most dangerous thing on here is tobacco, smoking cigarettes. If you have a pack and a half a day, you are getting close. 36 for a pack has 24, so you're saying a pack and a half, which is not an unreasonable amount for some people who smoke. Like, there's 4-packers out there. You light them off each other. As soon as one's done, you start the next one. So, all right, I have like one more thing to tell you on Monday about this. So I'll see you guys Monday, and then we'll review. So if you have review questions,